Okay, I'm from OpenPath also. This is called Deep in the Motherlode. This is a take two. Last year I made a new take and started doing the demos and I didn't have time to finish them. So I'll take the last part and do it in half an hour this time. This is my mail and we are still in Argentina and some other countries. Okay, this is after a new error, of course. We did, I show our ORP solution, how we handle proxies, and this time we're going to talk about how we manage caches. The problem is really easy to show it to you. We have more than 4 million users accessing our platform. The user case in the way the users connect to our platform is quite strange for the rest of us. We have a burst of calls of the same user for about 10 minutes, 15 minutes, and they disappear from our view, and they come back maybe today, maybe tomorrow. We need a lot of resources when a user connects to our platform to have in hand really close to the instance. And it's quite difficult to determine what we are going to need and when. So the user is part of an account. It has financial accounts, addresses, cards. We are a fintech solution so you can imagine how many data we need on each user, the latest activities, things that we need to have in hand just in case the front asks us for all that information. So we have at least 3 addresses for each user. There's a lot of information, and and working directly with the database is quite expensive. I mean, not only in pesos or dollars or whatever the money exchange you want to do, but also on resources, time. It's quite difficult to manage this amount of users getting at the same time. So we came with a wonderful solution. We created huge virtual machines and cache all the objects in memory. We managed to start each instance in about 23 minutes. That's a great success. I hope you all like it, and that's the end of the talk. Okay, now, we thought about this at the beginning when we had about 10 users, but it didn't scale quite nicely. So we have to go back and think for a while. And we have the concept of temperature. The temperature of an object for us, it's based on the user's frequency and when we are going to need it. It's quite important for us to determine how hot is an object and when we are going to need it. So the hottest objects need to be really, really close to the instance, and actually on each instance. So how are we going to manage so many nodes and so many virtual machines running each one instance, and we can get all the information at the same time, being that we are not sure that each user will get on the same node. So we have to sparse the data through something on the environment. We have a Kubernetes environment with, I don't know how many we have in production right now. If anybody knows that, let me know, but 50 nodes, I don't know. So we have two cache strategies. Uh, First one is quite simple. We just keep on the old-fashioned way. We keep some data on each instance on memory. This is data that it's not going to change frequently, and it's finite with countries, provinces, things like we will need eventually during any user call to our system. So we have some really few products where, and you can imagine, for example, rules that I have there. So they are finite, they are small, and we can keep them in memory the old-fashioned way. Some of them, all of them on each instance. And I said not so static because it can change. We can add a province while the system is running, of course. And I'm going to show you how we handle that because we handle it. We don't need to restart the instance, each instance, just because we added a province. And the nice part is incremental cache. What we do, and I'll show you in a minute, it's based on the temperature of the object, and it's going to be either all on the instance, and we have a centralized repository of cache, I'll show you in a minute, where we keep cached objects for all the environment. There are some questions that I managed to add at the end of some slides in case we come to the end and you don't know what to ask. Just you can copy and paste or remember and say those questions that I have on the last part of on the bottom of the slides. The static cache, I mentioned it, it's quite easy. We maintain the cache according to the operation. That's quite easy. If it's a delete, we invalidate it. If it's an update, we update it. That's not, there's nothing new in there. But that cache, that object could be cached on another instance. So keep that in mind. It's quite easy to just say, okay, I invalidate this object that I got from the database, and I get it again because it has changed. But, and this is important, it can be the same object on another image. And we'll talk about that in a second. The incremental cache is exactly, practically the same. We, on the insert, this is important, we keep them on the environment cache, we call it level 2 cache. On the instance cache and persistence. Of course, we use PostgreSQL as the database. On the delete, we invalidate both caches and delete it from persistence. That's nothing strange, and we are on the update exactly the same thing, but it could be on another instance. So we have a message broker. We chose RabbitMQ. We have a farm. It's a proprietary cluster above it, and we use it to send messages between instances. I'll show you the numbers at the end. It's pretty impressive how many messages it could handle. So each machine, each virtual machine that receives an update does something on the objects that it has in memory. And let me show you what we do. On the insert, we insert on the cache. When we receive a message, each node will receive a message saying, I modified this object with that object ID. So we the second level cache on memcache. You could ask me, why don't we use Redis, for example? I don't have that question right here, so I'll answer just in case you don't remember to ask me about it. And we use memcache because it's a key value, and we just store the key, that is our object ID, and a serialized object on the value on memcache. And we needed throughput, as much throughput as we can get. Redis is more complex. It gives you more options, but we just need speed. So we decided to go that way. On the incremental cache, this slide is a little more complex, but let me explain it to you quite easy. On an insert operation, we insert on both cache. Nothing changes. The other instances will find it, will select it or look for it, and they'll get it. But on delete, the instance that generated that delete or update, what it does is invalidate the objects and sends a message to the farm. The other instances invalidate the object and convert it to a proxy. So the next time they are going to notice that it's a proxy and will get it from the persistence. It's simple, but it took us a lot of time to implement it and make it work on a timely fashion, because it's quite hard to get so many transactions and a lot of things can happen. If you don't know what a two-phase commit problem is, I'll explain it to you and you can ask me that question later. Two-phase commit is when you need to write to two phases at the same time. What happens if we try to write to the database and write to the second level cache, and we fail to write to the database? You have to roll back the whole operation. It's quite difficult. So if you ask me that question, I'll answer later how we solve it. We have a time to live on each object, and we have a eviction strategy that we use to keep the objects that are hotter, as I told you, temperature. We keep that objects in memory, and the objects that are getting cooler are evicted from the cache. It's quite simple for us. It took us a lot of time to determine the times of the time to live. And this was a lot of usage of statistics and trying to get the times right for the whole system. Right now, we have, this is a snapshot of our, well, we use Grafana to monitor our platform. And this is a day in our lives. We have about 17 million. This is from one of our clients, the biggest one, let me say. So, but we have about 17 million API calls during that day. Some of these calls can modify up to 10 objects and the balance of the account. So we know we manage money. We know it's important to not lose a single transaction, and have a log of what of all we do. So we in this time we also log the transaction. So we have a read-only database and a read-write, and we manage all our transactions. This is on the Smalltalk side also. We manage where we do the different operations that we need to do, if we need to go to read-write or we need to go to read, and how we keep those databases in sync. The replica is really important that works smoothly. And on these particular days, let me show you how many, let me zoom here. We had 48 million messages moving through the environment from one node to the message broker, and the message went through all the rest of the instances that were subscribed to that kind of message. So you can imagine that every millisecond it's important for us, and we are really proud of what we did and we can tell with proudly that all of this is working on Smalltalk. So we are really happy. For us, it's a great experience, and we thank you all for that. Oops. This time I'm in time, and yes. I had to separate the talk in two parts, so and we have plenty of time. We can talk. So any questions will be greatly appreciated.
Hello, thank you for the talk. One question: when you talk about putting the object on the memcache, so you put the key or the ID, and then the serialized version of it. So just for me to get into the details, do you know which serializer you use? You using the object swapper from Vast?
What is the question? I'm sorry.
Which is the serializer that you use for
Stamp?
The
Stamp? Stamp is?
Storm.
Yes.
Okay. So that's text.
Yes.
Text-based.
Yes.
Okay.
Yes. It's memcache gives
it's
string.
kind of the JSON.
It's a string.
Yeah.
Yes.
Okay. Thank you.
For the deserialization, we had to work hard. I told you that. I'm sorry, since nobody is asking and we have 10 more minutes, let me complete the answer. It was really tough because if you are going to ask me how we can solve the two-phase commit problem, where we need to store in the database or store in the level 2 cache, is we delegate asynchronously to the database to store on Redis. I'm sorry, memcache. We had this discussion yet before, and we Postgre natively doesn't know how to deserialize and that object, so we have to manage to make it do that. Yes.
Just speaking about that serialization, how big or complex are the objects that you serialize using Stone? That's the first part. And the second part is, have you tested or tried just compressing that? Because
we made some, well, how long, it depends enormously on the object, but what we do is, I think we have a limit of 1K when we don't cache that object. I need to check the code, but I think it's 1K.
one what? Sorry.
1K.
Okay.
and the size of the objects varies a lot. I mean, a province it's a code and a province, but some other objects like addresses a little bigger. So it depends a lot. Most of the objects are small. We tend to keep the object as small as possible, but the transactions are becoming more big than we want. We are working on that. There were two questions, correct?
The second part was if you
if we try to
if you
compress it,
compressing that using one of the broadly
we
or
prefer to
LC4.
spend. Yes, we did, and it takes more time that we want to spend. We prefer to pay more for memory. It's something that we contemplated, but no, we need to be. For example, we did strange things that we managed the eviction. How do we know that the cache is up to date? For example, it's quite difficult. You can really know if you are using a cache object that is the object that is stored on the database. We did everything we can to be sure that that object is. Imagine that a node didn't receive an update and it has the previous version of the object in memory. That could be quite complicated, and we made a lot of work to be sure that that works. And it's impossible to verify that the object is the one that should be there on a platform base. It's too expensive to confirm that object. So on our eviction strategy, that is running concurrently with the instance, with the platforms, we do that. That the object, that the eviction really happened, that is that the object is not there anymore, that the object is the one that should be there. We store for each object an optimistic locking on memcache for the latest version of each object. We do a lot of stuff to make sure, but remember, we have little time to do that. So
yeah, I was going to ask, how often do you do the eviction process?
the eviction is running all the time. I mean, the eviction system is working all the time, but right now we are doing we tend to keep I think it's 20 minutes, the information on the level 1 cache on the instance, and we try to keep up to 2 days. It sounds like a lot, but we can do it, so we are doing it. Between 1 day and 2 days, the level 2 cache.
When you were talking about serializing the object, why are you doing that? Why are you storing on the cache the object as you get it from the image? Is that a strategic decision? It's just a simplicity one, or
we need really the fastest throughput that we can get. Memcache does that, and it just saves keys and values, and the values string. So we have no other way to store an object in so little time in any other place that in memcache serialized.
okay, but that you don't need another format for that object.
We can't save it on any other format on memcache, and it's the fastest one.
Okay.
So I understand why do you serialize it, because it's cheaper to serialize it and store it in memcache than any other thing that we tested. So we decided we need to serialize it and save it there, and it's cheaper than any other thing. So I understand the question. I mean, why don't you just dump it anywhere? Because we don't have anywhere. We don't have another thing that is faster than that. Okay. Thanks a lot.